Please welcome to the stage from the Bar-Ilan University in Israel, Mr. Zeev Zalevsky.
Good morning. Good morning, Kosovo. I would like to thank the organizers for inviting me to speak here today. So, as introduced, my name is Zeev Zalevsky. I'm from the Faculty of Engineering at Bar-Ilan University. And today, I'm going to speak with you about the topic that I like the most to speak about. My favorite topic. I'm going to speak with you about myself. And more specifically, I'm going to speak with you about my personal way in the world of entrepreneurship. And I come from the field of electro-optics. So we will hear about light, we will hear about entrepreneurship, and I hope we will finish in half an hour, okay? So before we start with entrepreneurship, you need to understand that being an entrepreneur, going through this path, is like running a marathon. And when you run a marathon, the best methodology is to start as fast as you can, the fastest as you can. And with the kilometers, with the miles, slowly, slowly to increase your pace. Okay, so some personal notes. When you try to develop your own entrepreneurship activity, there are several things you need to be aware of. First of all, you need to be creative. You need to have the capability of improvise. You need, and this is very important, not to be afraid of making mistakes. Actually, you do a lot of mistakes when you establish a startup company. And of course, another very important thing is that if you want to build your startup company that should also be funded, you know, money, it's important. You should know how to speak with venture capitals. And by the way, if there are venture capitals in the room, so I'm sorry, this is better. And of course, something which is, again, extremely important is that, as Edison said many years ago, is that you need always to be optimistic and not to lose hope, because there are a lot of problems along the way. Obviously, it's not only about you. You need to have the right infrastructure to succeed. You need to have a lot of imagination in the environment that surrounds you. And you know, Albert Einstein said that the imagination is indeed more important than knowledge. So you bring knowledge, but you need to have an environment that supports imagination. And of course, before you start, don't forget that being an entrepreneur might sometimes be a bit dangerous. So those are my insights from this world. Don't forget to fail. If you learn from your failure, then you improve yourself and you gain experience. Never to give up. Always choose the right partners, because establishing a startup company in a way is like a marriage. You need to support each other in difficult times, and there are a lot of difficult times. And one of the most important comments I have is that it's not about the money. It's not about the final point. It's about the journey that you are about to pass. And if this is indeed your purpose, then you have better chances to succeed, although the chances are not very high. They're approximately 1 to 1,000. So, given that, let me tell you a little bit about my personal journey. I will start with the past, go to the present, and then continue towards the future. Prediction is a very complicated task. Albert Einstein said that predicting is very complicated. If you try to predict the past, then it is complicated. If you try to predict the future, it is really complicated. So I will go through my past journey, through the present journey, until my future plans. And I hope you will enjoy. So my first startup company that I co-founded was a company in which we had a magnificent technology. This technology was a technology of electro-optical switches that were able to switch light about about 1,000 times faster than other existing switches at that time. It was really exciting. The technology was amazing. We were working very hard. You can see here, the laser pointer is not working, but you can see here the first prototype that we were going to ship, and we were so excited that we dropped the box and the prototype was destroyed. Eventually, this company was sold to a Brazilian communication company called Patec. But what my lesson was from this specific activity is that it's very important when you develop a technology to know if there is a need for that technology. Here specifically, we developed switches that were 500 times faster than any existing switches in optical communication. The problem was that you didn't need the switches to be faster in optics communication because the main application for those switches was for the purpose of protection, and for that you had to have a switching speed of, say, few milliseconds. We were able to do it in few tenths of nanoseconds. So this is one important lesson that I have learned. Then I continued my journey, and we were developing a Pico projector. We thought it could be very interesting. Instead of having, you have computers, you have screens. What really limits the size of your computers is not the processing card, but rather the screen that you have. So we have decided to develop a small Pico projector like the one you see here that will project the image you want to see instead of using a screen. And then if you connect it to phones, at that time there were no smartphones, or to a computer, you could really have something very compact to carry with you and have a screen, a virtual screen with very high resolution. But in order to have a screen with high contrast, to do this, you had to have strong sources to project the image in this Pico projector. We were the first to do it with laser light. The problem is that at that time, which was many tens of years ago, laser technology, people considered it as something very dangerous. Today, no, you use lasers almost everywhere, but we were premature. I mean, today you have Pico projectors based on lasers, if you don't know, but at that time, people didn't want to accept something that projects laser light into their eyes. This company was eventually bought by Kaga Electronics. My next adventure, which is related to my third lesson, was in a company called PrimeSense that was eventually bought by Apple some years ago. What we were developing there is photonic technology to do precise three-dimensional sensing. The idea was to use it for gaming purposes. If you remember, I don't know how old you are, the Kinect module, which is connected to Xbox, is this. It worked actually very well. The optical technology was very interesting. Everything was very interesting. My specific mistake there is that I left too early. So you need to stick to the final goal until the end. And this was a very successful startup. My next adventure was related to the world of ophthalmology. Ophthalmology is the field of science which concerns each and every one of you, because we have eyes and our vision is not perfect, and we want to correct those visual discrepancies that we have. Now, the problem we tried to address in Exceed Imaging, that was eventually bought by BHVI, was the problem of presbyopia. Do you know what presbyopia is? So presbyopia, I see only people that are above 45 that say that they know what it is. Indeed, it is a problem or a situation that happens after age of 40 plus. It's a visual problem that I call actually an orthopedic problem. It's an orthopedic problem of uncontrolled shrinkage of hands. Uncontrolled shrinkage of hands. Do you have uncontrolled shrinkage of hands? I will explain what I mean. When you are 30 years old, you want to read something, you hold it here and you read it. When you are 40, you hold it here and then you read it. When you are 45, you hold it here, you read it, and then when you are 50 or 46, you say, oh, I cannot read it, my hands got too short. So the point is related to the fact that our eye can have a very good vision for far away, we can be hemotrope, but when we want to read something, to focus on something which is nearby, close to us, we need to change the focal length of our eye. This is called accommodation. The problem is that after age of 45, we lose this accommodation capability. Now, in spectacles, there are some solutions for that. It's called multifocal lenses. The problem with multifocal lenses is that in order to see in focus, you need to pay with your lines of sight. So you have along the area of the glass, you have different focal lengths, and you need to choose the right line of sight to look through the right region of the glass, of the lens, such that the object in front of you will indeed be in focus. It's not very convenient. Some people don't wear glasses, I mean spectacles. They wear contact lenses. In contact lenses, the situation is even worse. You do have what is called bifocal contact lenses. They give you the capability to see in focus near and far objects, but not objects which are in the intermediate range. And in interocular lenses, the lenses that are being implanted in the case of cataract surgery, the situation is even worse. Again, you have what is called bifocal intraocular lenses, but still you cannot see things in the intermediate range. And also those lenses usually suffer from low energetic efficiency, which affects people, for instance, when they try to do things at night, like driving. We have developed a unique technology in which we took the lens and we did special scratches on the surface of the lens, and those scratches enhanced the depth of focus of those lenses, no matter what the lens were. It could be spectacles, contact lenses, or intraocular lenses. It enhanced the depth of focus by 3 diopters. Now, what is 3 diopters? It's exactly what you need to see everything in focus, from near to far. Diopters are the units that you have for your spectacles, and 3 diopters means that you will be able to see everything in focus from 33 centimeters to infinity, which is enough to read as well as look on faraway objects or anything in the intermediate range. So we extended the depth of focus of the lens, and no accommodation is needed anymore, and it is obtained over the full field of view. What is also interesting is that the same solution could be used not only for solving presbyopia, but also to solve various aspects of astigmatism. Astigmatism is when we have a different focal length along different axes of the lens. If the astigmatism is regular, you have cylindrical lenses that solve it for spectacles, or toric contact lenses for contact lenses. But if the astigmatism is irregular, you don't have a solution, but extended depth of focus does solve it. And we have developed this technology. So this is regular lens, this is its focus. We added the scratches, and by doing that, we extended the depth of focus. The depth of focus was much larger, and when it was larger, no more accommodation capability was needed. You can see here an example how, so what you see in the lower part of the slide is a zoom image of what you have in the upper part of the slide. So without doing extended depth of focus, you see the remote objects in focus, but the business card is unreadable. But in the right side of the slide, the remote objects are focused, but you can now read the details on the business card. And this is in the case of ophthalmic resolution charts. And we did many experiments of this technology, both for spectacles, like here, for contact lenses. This is, by the way, how contact lenses with those scratches look like. Those are clinical trials, as well as for RGP. RGP are rigid contact lenses, as well as for interocular lenses. And you can see here a comparison with the extended depth of focus lens versus a common commercial available bifocal interocular lens. And the main difference is in the intermediate image plane that is not in good resolution for the bifocal interocular lenses, but in good resolution with the extended depth of focus technology. So it was very, very interesting technology. And my specific lesson from this is that when you work with big organization, as a startup company, you need to be careful how to navigate your progress in a proper way such that you keep your control and yet you progress in your R&D path. And there is a saying in the Israeli startup ecosystem, and the saying is that two people meet. One has an idea, and he is a new entrepreneur, and the other has experience. He doesn't have an idea, but he has experience. It's not his first entrepreneur activity. They meet and they talk, and then each one goes to his own way. Now the guy with the idea has an experience, and the guy with the experience now has a new idea. So you need to properly navigate your path when you connect large entities, which are not always looking for your best interests. So this is my past. As you see, my past is very rich. You see my white hair. Now let us speak about my present activity. Are you familiar with Star Trek? You do. Good. So it's a science fiction movie, right? And if you remember, in this science fiction movie, in this spaceship, there was a medical doctor, and he had a device. The device was called a tricorder. A tricorder was a device that the medical doctor was pointing to subjects, and he could, to people, to creatures, not all of them were human, and he could diagnose their medical condition from a distance without touching them. So I have good news for you. This is no longer science fiction, only science, not fiction, not a fiction anymore. So we have developed very interesting technology that is developed in one of my startup companies called Continuous Biometrics, or Donisi Health. The technology has started in my laboratory in a collaboration with a colleague from Spain. His name is Javier Garcia. Those are the first prototypes that were relatively large. They allow to do monitoring from large distances of up to 400 meters away. I will tell you in a second how it works. And then, with time, we were able to reduce it to very small prototypes. And when the technology was commercialized to a startup company, to Continuous Biometrics, it was developed to various types of low-end as well as high-end prototypes, as you can see here, even as an add-on to a smartphone. Now, how does it work? At that time, when people were trying to do medical monitoring, the sensors were in such a way that you wanted to monitor a certain biomedical parameter, so you had a sensor that its physical operation principle matched to the physics of the biomedical parameter you wanted to monitor. But in order to do a good medical diagnostics, it's not enough to monitor one biomedical parameter. You need to monitor many of them. But it's not practical to take 20, 30, 40 sensors and to expect that the person will collaborate with those sensors and allow them to measure him. You need to develop one sensor that will measure one ring that will rule it all. One sensor that will be able to measure many biomedical parameters at once and then do a more reliable medical diagnostics. Now, but the problem is that every biomedical parameter has something different that specifies it. How can we build a sensor that can measure very different biomedical parameters at once? So we were thinking about what is the common denominator to almost anything in biomedicine. And the common denominator is vibrations, or let me call it nano vibrations. If you can measure vibrations with nanometric precision, then you can measure everything. Because vital bioscience, like respiration or heart beating, those are vibrations of your chest, blood pressure, vibration of the tissue next to a blood artery. But not only vital bioscience. If your precision is really nanometric, then if you have concentration of different chemicals in your bloodstream, the flow of blood, the pulsation will slightly, the vibration due to the pulsation will slightly be different. You know, nanometric precision, 1 nanometer is the size of a molecule. And if you want to measure, this is called hematology. If you want to measure hemodynamic activities, which means characteristics of flow of blood to different organs, again, those are vibrations because the flow of blood is accompanied by the pulsation of the blood artery due to the operability of our heart. So we said, let us measure vibrations, and actually, after developing the technology for 15 years, we discovered that Albert Einstein said exactly the same thing. So he said everything in life is vibrations. I cannot agree more. He copied it from me, of course, but still. So what was the idea? The idea was to take the sensor involved a laser, a camera with special optics, and some special image processing algorithm. We illuminated the tissue with a laser light, and the backscatter light was collected through special optics to the sensor. Now, the backscatter light forms, because laser has the property of being spatially and temporally coherent, the backscatter light forms a self-interference pattern which is called secondary speckle pattern. It's a random pattern. And due to movements and dynamic processes in the tissue, this pattern is randomly changing. So we had a special optics that caused this pattern to change according to specific rules, to follow specific rules. The AI algorithms analyzed the image, and from this they could extract the 6 degrees of movement occurring in the tissue versus time with a nanometric precision. And it was very useful, and we have applied it to various applications of smart homes and smart cars and sleep clinics like sleep apnea. It's a big problem. And all this monitored the nano vibrations, which were translated to a set of biomedical parameters, which were translated to a medical diagnostics for various applications, applications of IT and so, smart homes, as I said, cars and so on. One of the things that I mentioned for this technology is to sense hemodynamic activity. So a few years ago, I wanted to try and use this technology that we have developed in order to remotely sense brain activity. Now, how can I sense brain activity? Apparently, when we operate our brain, the brain needs oxygen. How the oxygen gets to the specific part of our brain, it comes with the blood. And if there is a flow of blood to a specific part of our brain due to the activation that we are doing, it means that there is vibration. This is the hemodynamic capability of our sensor. By the way, the alternative today to sense brain activity is, say, FNIRS or EEG recording. Both of them require wearing a helmet like the one you see in this picture. We wanted to do it from a distance, but we are measuring nano vibrations, and we managed to do it. So you can see in the left upper part one of the experiments where the sensor is behind the head of a subject, and we measure nano vibrations. You see here A, B, and C. Those are 3 different subjects. What we were doing with them, we were stimulating their visual cortex. It's around here. We were not stimulating, then stimulating. No stimulation, stimulation. You can see, for instance, in A, B, and C, 3 different subjects, no stimulation, almost no vibration. The stimulation started, you see the black line, which indicates that flow of blood went there. So we know that the person is trying to see something and to understand what he's seeing. We know it from a distance. Then we try to test another cortex, not the visual cortex, the short memory cortex, which is here. close to the forehead. So we gave different memory tasks to one of the subjects, and we analyzed the flow of blood to the forehead. And you can see in the experiment, the blue line is the baseline, and the brown line is what happens when he tries to remember to accomplish the memory task that we give to the subject. And what I'm recently doing, again with quite interesting results, yet in the academy, as being a researcher in the academy, what I'm trying to do is to sense senses. So what we do, we stimulate different senses, like smell, like hearing, taste, sense. All of them are around this region. You know, people have 5 senses. I personally have 6. I have also a sense of humor. So we were stimulating the additional 3 senses in addition to visual sense that I mentioned before, and we are monitoring from this region, and we could now identify that indeed, and we compared it, of course, to an EEG reading as a reference, as a medical reference. All the measurements are always done with the right medical benchmark, and we could see that indeed there is a very good correlation. The next step that I'm trying to do, it's not in the slide, I will try to really read thoughts. Really to see, not only to know that you stimulate a certain cortex, but to know whether, say you stimulate the visual cortex, what is exactly that you are trying to see. But this is for the next year event. Okay. Another interesting activity, present activity, is related to a startup company called Zeev. And there we have developed a microendoscope for medical usage, a disposable microendoscope, which is as thin as the human hair. But the thickness of this endoscope, which makes it so minimally invasive and disposable, doesn't come on the extent of its resolution. On the contrary, its resolution is actually better than the medical benchmarks of endoscopes being 3 millimeters in diameter, but ours is like 100, 200, 300 microns. Very, very thin. You can see here the advantages, the features, examples, or images from the endoscope. And of course, we did a lot of experiments in the laboratory before the technology was commercialized. For instance, you can see here experiment that we did in the left upper part of the screen, an experiment we did in which we tried to do imaging of deep cortical layers of a mouse, of a rat. So we drilled through the dura, and the endoscope was inserted into the brain. It's so thin that it was minimally invasive. The rat was acting, and we could image blood arteries in deep cortical layers. It's very difficult to do it because it's in deep cortical layers. So we were using rats. Sometimes I use students, sometimes rats, whatever is available. It's a joke. Okay. Another interesting technology is that I'm currently working on, a commercialized technology, is related to the capability of significantly reducing the dose, the radiation dose of X-ray and gamma imaging machines in order to expose the subjects to smaller radiation and also to protect the medical doctors that need to repeat those procedures many times per day. And the idea was to develop, I will not go into details because I don't want, the chair tells me to speak faster. So to finish, excellent. But we were able to reduce, in the prototypes we built, to reduce the radiation by 4 times, and the capability is to do it by even up to 1 order of magnitude or even more than this. The last thing that will tell you that I'm currently doing is I'm in a startup that we have recently established, is developing a photonic processor which operates inside of a fiber that can consume less power and work several orders of magnitude faster than the way the regular computer can work. You can see here some examples. Now let us speak about the future in 10 seconds. One of the projects, I try to develop spectacles that will allow blind people to see by translating the image that is collected by the spectacles to spatial, tactile stimulation of their cornea. It's like reading Braille that blind people read with their fingertips, to read Braille with their cornea but without the need of reaching their eyes forward because the image comes through the camera, we have already very promising initial results. I do also things related to nanophotonics. We have developed special nano antennas, really small, nanometric, that instead of, say, taking a CPU, inside of CPU you have what is called cross-connects that connect different processing units to each other. This consumes energy and has some interference noises. We do wireless communication, nano communication. So we do those nano antennas inside the processor and transmit information from one processing block to the other without having the connections. This is my last slide. We also develop smart clothes for elderly care. Thank you for your attention, and I will finish at this point. If you have questions.
Fantastic. Thank you so much.